type of representation for the coupling between the electric resonator and microstrip, we can arrive in the end to such representation where you see that when the electric resonator resonates, we have here a shunt resonance circuit. When this resonance circuit resonates, what remains is only this R equivalent, which connect the two sections representing where the coupling happens between the electric resonator and microstrip. Actually, this equivalent resistance is extremely large compared with the characteristic impedance of the microstrip, and then is practically equivalent to an open circuit. And then what happens is that when the resonator resonates, we have in the section where this equivalent circuit is valid, we have practically an open circuit. For instance, making a simulation of this configuration, varying the distance dx between the electric resonator and the microstrip, and observing what is the reflection coefficient at the input of this line, it can be observed that just around the frequency where the resonator resonates, we have a reflection coefficient which is in magnitude quite close to 1, which means open circuit. All the power is reflected back. But it is sufficient, a very small displacement from these resonant frequencies, that the reflection coefficient becomes very small. In fact, when the electric resonator is transparent, what remains is a transmission line closed on its characteristic impedance. So, without the resonator, we see gamma in quite close to 0. So, we can exploit this type of behavior because we have a very, very fast change of gamma in from a magnitude, a large magnitude around 1, up to a very small magnitude quite close to 0. Why we can exploit this? We can exploit this because we have seen that the stability of an oscillator is quite related to the variation, to the rate of variation of some particular parameters associated to an element determining the oscillating frequency. And when this happens, we have the possibility to bound, to constrain the oscillating frequency just around where this very fast change of the element parameters happen. Sorry, close the door. Okay, let's see what way we can exploit this factor. In other words, how we can exploit the fact that only around the resonant frequency, that is when the electric resonator is coupled to the microstrip, we can have a very large reflection coefficient. The idea is, well, we can assess the situation, the parameters of our oscillator in a way that only when this gamma in is close to 1, the oscillating conditions are verified. Instead, when we move from this condition and we go close to 0 as a reflection coefficient, we have to set up the situation, set up the parameters of the circuit representing the oscillator in a way that the oscillating conditions are not verified. We can just exploit this fact, and then we make a constraint, a bound to the oscillator to working only in the range of frequency where gamma is quite close to 1. Okay, then this is the scheme I'm discussing of. This is the classical configuration of the oscillator, and the input as a network A. We just are using what we have seen before, that is a transmission line closer to 50 ohm. When there is no coupling to the resonator, to the dielectric resonator, we see here a matched load, that is gamma in equals 0, and what we have to do is to have a device which, with gamma S equals 0, doesn't have gamma out, this one, larger than 1. If this happens, oscillation cannot be erased, and then we are sure that only when gamma in is quite close to 1, this structure can oscillate. Okay, this is the equivalent representation of our structure, and as I said before, we want to get gamma out larger than 1 in a very narrow range of frequency around omega 0. If this happens, we know that the final oscillation frequency will be inside this range, only inside the range where gamma out is larger than 1. And this range is just close to the resonating frequency of the dielectric resonator. This is an example in order to show this. Okay, this is the way we have represented the dielectric resonator, and this is the oscillator scheme. For the dimensioning, as I said before, we have set this length in order to get gamma A, giving this value of gamma A in order to have Z out larger with a negative real part, and then gamma out in magnitude larger than 1. Then we have imposed the usual rule that ZL is about the real part equal 1/3 of this, and the imaginary part is equal and opposite. With this value of ZL, we get the ring lower than 1, and then the oscillating condition in this situation is satisfied. This, I repeat, are the condition where the oscillator resonates, placing here an open circuit, and then determining with a distance phi from the open circuit a reflection coefficient gamma A given here. So we have designed the oscillator just at the frequency where the dielectric resonator resonates. Now let's see what happened versus frequency. This is the representation of the output impedance of here is the output impedance observed at the output of the active device. We know that oscillation can happen only when this impedance has a negative real part. So if the range of frequencies where the negative real part is very small, we know that also the range where the oscillating frequency can happen will be very, very small. And so the system will be stable. Okay, you can see here the real part is the red curve. You see that the range where the oscillating frequency is negative, where the real part of Zin is negative, is only this one. But this range is extremely small. Let's observe the scale. We go from 4.98 up to 502. This is in the order of few megahertz at 6 gigahertz. So what we will obtain is a very, very, very stable oscillation, which will be inside this very small range. Actually, we impose 6 gigahertz, okay, 5 gigahertz, okay. But at the end of our transient, we are not sure that the oscillating frequency will be exactly 5 gigahertz. However, it will be inside this range. And back this range extremely small, actually, the frequency will be very, very close to 5 gigahertz. Okay? And moreover, it will be constrained to stay inside this range. So this is the reason why this solution is very stable. Because we are constraining the oscillation to stay inside this very small range. Okay, this is an example. This is the verification by means of the particular probe available inside MicroOffice. We show the spectrum, the type, the time domain results, and so on. We can improve this by placing a resonant circuit at the output of the oscillator scheme. Okay. Okay. Here, in fact, I have used a sort of of harmonic traps. What means harmonic traps? These are elements that resonate in reporting here a short-circuited the harmonics of the oscillating frequency. As we have seen last time when we had discussed of this solution, in this way, only the voltage different from zero may happen at the fundamental frequency, because at the harmonic, the second harmonic, third harmonic, these two, this is the second, this is the third harmonic, the voltage cannot be different from zero, because here we have reported that this frequency is short circuit. So we can improve noticeably the spectral contents. We remove the high order resonances of our fundamental oscillating frequency. Okay? Okay, that's all. Do you have questions about this? Is it clear? You asked me to revise this, okay? Other questions about this topic? No? Do you have a particular topic that you want to revise together? There is some topics in the second part that is not completely clear, that you want to revise, please.
The part of the Eigen networks.
Eigen networks.
And how connect the impedance that we look in the even and odd networks to the impedance matrix and scattering matrix.
The relationship between the Eigen networks and the impedance matrix. Okay. I don't remember if this is the last one or not. So just a moment. Yes. Okay, first of all, what is the meaning of eigenvectors and eigenvectors of a matrix? The meaning is only mathematical, so there is no particular consideration to do. If I have a square matrix S, I can evaluate analytically its eigenvalues and eigenvectors by means of the solutions of these two equations. The first one determines the eigenvalues. The solution of this linear equation gives for a matrix S of order n, gives n complex values if the matrix elements are complex, which are called the eigenvalues of the matrix. Okay? For each eigenvalue, there is in correspondence an eigenvector, which is a vector of length n, which is a solution of this homogeneous system, where S is the original matrix, S lambda, sorry, is the eigenvalue, and x lambda is the vector representing the eigenvector, whose solution represents the eigenvector. For a given matrix, we have of order n, as I said before, we have n eigenvalues, and for each eigenvalue, we have n eigenvectors. For each eigenvalue, we have a corresponding eigenvector with n elements. The eigenvectors, moreover, are not univocally defined, because this is an homogeneous equation. So if you have a solution x lambda, there is another one k times x lambda. So the eigenvectors are defined unless constant, arbitrarily constant. Okay? Now this is the mathematical aspect of the matter. But what is the physical aspect in the case of a circuit? The physical aspect is easy to say. Actually, if the matrix S represents an impedance matrix, an admittance matrix, a scattering matrix, the eigenvector of that matrix represents a set of values for exciting the ports of this matrix. So once I have evaluated for this matrix, obviously of which I know what is the values of S, I have computed the values, the eigenvalues, the eigenvectors. Well, I can use these eigenvectors as exciting waves, exciting voltage, exciting current, depending on the type of matrix I am considering. Okay? Then what happens? Let's suppose that you have then a scattering matrix. It's more easy to represent then. Here is the scattering matrix. These are the ports I am considering. Well, an eigenvector, let's suppose x lambda at, will define then the entering power wave. These are x lambda 1, x lambda 2, x lambda 3, and so on. Then these are the exciting set of waves. To this value, there will be an eigenvector. To this eigenvector, there will be in correspondence an eigenvalue as lambda. Okay? Well, what is then the properties? The properties is that if I consider the reflected wave at each port, and they take, let's suppose that this reflected wave are x beta 1, x beta 2, x beta 3, and so on. Well, the property is that the ratio between x beta I divided x lambda I is for all the ports the same and is equal to S lambda. So all the ports present the same reflection coefficient, and this reflection coefficient is equal to the eigenvalue. This is the property corresponding to the mathematical definition of eigenvectors and eigenvalue. Okay, this is a property, okay, but in what way I could exploit this property? Well, for a general network, is unuseful because I cannot exploit this property. The reason is that I don't know what is the eigenvector for a general arbitrary network. The values of the eigenvector are unknowns. It depends on the scattering matrix. But if I want to get the scattering matrix as a function of the eigenvalues and the eigenvector, obviously, if I don't know what are the eigenvector, this knowledge is absolutely unknown, unuseful. Okay? There is, however, a particular case when only by induction I can obtain immediately what are the eigenvectors. This happens when there are symmetry, axis, symmetry plane in my physical structure. When this happens, I can immediately say what are the values inside the vector x lambda. For each eigenvector, I can immediately obtain the excitation I have to apply to my network in order to get the first eigenvector, the second eigenvector, and so on. In what way I can derive by induction the eigenvector? Simply by placing symmetry plane by replacing, the symmetry plane with electric or magnetic boundary condition. Okay? Let's suppose to discuss this for a 4-port network, which is more easy to deal with. But this can be done for whatever order of the network you are considering. Okay? Well, in the case of a 4-port network, which is completely symmetric, there are two symmetry planes. And to this two-symmetry plane, I will have 4 possible combinations of electric and magnetic condition, boundary condition. In other words, I can set this plane E or M, or sorry, open or short, this plane open or short. In correspondence to each of these conditions, I know what is the eigenvector I have to use. As I said before, eigenvectors are defined at least a constant. So it is not relevant what is the absolute value. I can set, for instance, +1 for open circuit and -1 for short circuit. So if I set here open, this means that I am setting the eigenvalues 0 for the vertical plane and 1 for the vertical plane and 1 for the horizontal plane. Well, in what way I can obtain this condition? Let's suppose that you are just in this condition, okay? Open here and open here. Just due to the fact that this structure is symmetric, I know that in order to have in the middle of my structure an open circuit, I have to excite both sides with the same signal. And this means that these two components of the eigenvector I'm considering are equal to +1. The same here and here. If I want to have in the middle an open circuit, I have to excite these two ports with the same excitation. And then also here, I have to be in this condition. This means that this eigenvector, its lambda, will be given by 1, 1, 1, and 1. Okay? Instead, if I have in this vertical plane not an open circuit, but a short circuit, what is different with respect to before? Let's suppose that here we have a short circuit in the middle of this plane, while this one remains an open circuit. So, if I have an open circuit here, the excitation here and here must be the same again. But if I have a short circuit here, the excitation here and here must be opposite. So here I could be 1 and here -1. Okay? This is the situation where this is in the vertical plane I get a short circuit, and the horizontal plane I get again an open circuit. And so in this case, this port will have -1 instead of 1. And so on. There are 4 combinations, and each combination define an eigenvector. Is it clear up to now? Well, now this is important because at this point I don't have to know what are the values of the scattering matrix for evaluating the eigenvectors. I have the eigenvector only by induction, as I said before. They are plus or minus 1 combinations, okay? Well, at this point, however, I have to evaluate also the eigenvalues if I want to have the complex situation. And what way I can use in order to get this information? Again, I can exploit here what happens when there are a magnetic and electric plane defining an eigenvector. Let's suppose just that we are in this situation where all the open circuits are defined. If we are again an open circuit, here I have an open circuit, you have 4 elements in my structure which are all the same. So you can consider only 1/4 of my structure having here an open circuit and here an open circuit. Okay? This configuration, observe this port, here the second terminal is always ground, okay? So we have only one terminal as a reference, okay? So looking inside in this port, what I am observing, for what I said before, what I am observing this port is just the eigenvalue. No? What I said before is the general property of a eigenvalues and eigenvector is that when I excite a network with an eigenvector, what I observe at each port, considering the parameter associated to the matrix, what I observe is just the eigenvalue. In the case of the scattering matrix, then, if I excite my structure with an incident waves which correspond to a given eigenvector, what I observe from this single part of my original structure, that is the reflection coefficient I observe here, is just the corresponding eigenvalue. So I can obtain the eigenvalue corresponding to the eigenvector I have used for exciting my network by extracting the part of the network which remains once I have inserted electric or magnetic planes associated to the eigenvector, and then observing inside this network the value of the reflection coefficient, I have the eigenvalue. So in conclusion, only by induction and by deriving the eigennetwork from the excited network with the eigenvectors, I can obtain the reflection coefficient that corresponds to the eigenvalues. We are revising this concept, but this should be, I think, clear in order to understand what is the procedure for obtaining eigenvalues and eigenvectors. Actually, perhaps the most critical one is the first one. Identify what are the eigenvectors by induction. But as I said before, it's relatively simple because they correspond to have placed an electric or magnetic fields in correspondence of the symmetry planes. So it's not so complex. Once you have this, what we have to do is only to extract from the network the part which remains once we have inserted physically, open a short circuit along the symmetry plane. Okay? The example is trivial. Just in this case, let's suppose that you have to do with a network like this one. This is a 4-port network, okay? What are the eigenvalues? These are the two planes, okay? So I can split this one into inductances, L divided 2, L divided 2. Here, two capacitance, 2C, 2C, and the same here, 2C, and 2C here. And you have the same, L divided 2, L divided 2, okay? If both of them, these planes are open circuit, what I observe here? Here there is an open circuit, here there is an open circuit. What remains is something like this. Open, open. What do you observe here? What is the impedance observed looking into this network, this structure? This is open. This is open. Then, what is the impedance? Infinite. There is no path for the current to go to ground. So the impedance is infinite. And then gamma lambda is equal to 1. Because it is an open circuit, no? And then you can try to all the other combination. For instance, if this is a short circuit and this is an open circuit, the difference is this one. And then at this point here, I have L divided 2. And then the impedance is L divided 2 multiplied omega 0. And gamma will be the corresponding reflection coefficient. And so on for all the other. So it's trivial to get at the end what are the eigenvalues of the network once you have identified the eigenvectors. The last step is how to relate the eigenvalues and the eigenvectors to the matrix. But also in this case, the answer is relatively easy, because what we have to do is to remind what is the definition of the the scattering matrix or the impedance matrix or whatever you are considering. In the case of the scattering matrix, you know that the reflection coefficient at port 1, for instance, is A1 times S11 plus A2 S12 plus and so on. Okay? Let's consider the case of a two-port which is very immediate and easy to report. Well, when I am exciting my network, in this case a two-port network, with an eigenvector, I can replace A1 and A2 with the values corresponding to the eigenvector elements. Let's suppose that the first eigenvector is A1 equal A0 and A2 equal A0, are equal in phase. Then I get B equal A0 times S11 plus S12. And then B divided S0. What is B divided S0? I'm exciting with the eigenvector. Then B divided the exciting elements is the eigenvalue. So is S lambda 1 equal S11 plus S12. In the same way, if I'm exciting with the other eigenvector, which is this one, minus A0, then the difference is that here I have minus, and then S lambda 2 will be given S11 minus S12. Okay? These are the relationship between eigenvalues and scattering matrix elements. From here, I can get then S11 S lambda 1 plus S lambda 2 divided 2, and S12 equal S lambda 1 plus a minus S lambda 2 divided 2. So these are the concepts. You can extend this to whatever order you want. Okay? Other questions about this? Okay, other topics you want to refresh? We can comment together the past exam, second midterm exam of the last year.